We have already seen some hints about a relationship between residues on one hand and the contour integral of a function on the other hand. Now let's make this more concrete in the very famous and useful residue theorem. So what's going on here? We have again a complex function f of z, which is analytical everywhere inside a closed contour C. So this is C. So C is analytical everywhere inside C except for some isolated singularities. So for example, singularity over here, singularity over there. So if you say isolated singularities, think for example about poles. So really a singularity confined to a single point. We're not talking about a branch cut, which is just a continuous set of singularities, one next to the other. Okay, so that's the situation we have. We have our function, we have a set of isolated singularities inside. The residue theorem tells us that we can calculate the contour integral of f of z dz simply by taking the sum 2 pi j and then the sum of all the residues of all the isolated singularities inside. And if at some later stage we find a shortcut to calculate these residues without calculating the contour integral, then we have found a very nice way of calculating that contour integral. Good, so that's the setting. That's the residue theorem. How can we actually prove that? Turns out it's not so difficult. You can again use Cauchy's theorem for that. Now for Cauchy's theorem, we need a contour where the function is holomorphic everywhere inside. And for this particular contour, that's not the case because we have these pesky singularities there. But we can play a trick that we have already played a couple of times in the past, which is to move to an extended contour where we just cut out these singularities like so. So here we have an extended contour where now the singularities, the problematic points, are outside of our contour. And again, just like before, we will be taking the limits of these two straight sections becoming infinitely close together such that we recover the original contour here in the limits. So what I suggest you do now is pause the video, apply Cauchy's theorem on this extended contour, and then see if you can prove the residue theorem. So Cauchy's theorem tells us that the integral over the extended contour is equal to 0. And let's now just write down all the different contributions to that extended contour. Of course, one contribution will be our original contour C, so f of z dz. In the limits of everything moving close together here, we will recover our original contour C. And then we have all of these pairs of straight line segments. And again, in the limit, they will cancel because we move through these straight line segments in opposite directions. And we have a continuous function, so they will all cancel. And then finally, we have these little circles around our singularities. Now, let's call these contours, for example, C0 and C1. And by definition, if you write down something like the contour integral over ck f of z dz, by definition, we mean then that ck is positive in the counterclockwise direction. Now, in our case, if you look at it, we need to traverse these contours in the clockwise direction. So that means that we have a minus sign in front of them. And then we just sum up all the different contributions from all of the different residues. And the end result is 0. And now we're basically finished, because if you go back to the video about the definition of the residue, you will recall that this integral over here is nothing more and nothing less than 2 pi j, the residue of the function at the point ck. And then just throwing all this stuff to the left-hand side, and then we basically have the proof of the residue theorem. Very important theorem that will help us to calculate real valued integrals in a much more efficient way, as we will see later on, but one step at a time.